Next talk is by Professor Littman, a professor of computer science at Brown University. He has earned multiple awards for his teaching and research, and he has served on the editorial boards of the Journal of Machine Learning Research, as well as the Journal of Artificial Intelligence. Today, he will be speaking about the 4 ways we can tell machines what we want and how we can do them better.
Great. Well, thank you very much for inviting me. I hope everyone's day's been going okay. Yeah, we'll sort of see how this goes. This is a talk that I worked out for you guys, and haven't tried on anyone else yet. So this is a bit of an experiment. So feel free to stop me, ask for clarifications. I have 2 screens in front of me now. One that I can use to see my slides, and one that I can use to see the chat. If anyone wants to type questions at me, I will see them. And I guess you can also, I don't know what you've been doing the rest of the day, but if just unmuting is your preference, that's fine as well.
Yeah, so, either one should work. Yeah.
Right. So yeah, thanks again. So I'm going to be talking about 4 ways we tell machines what we want and how we can do better. And I think, I don't know everyone's background, obviously, but I'm hoping that what I will cover will include things that you already know, but maybe are going to see from a slightly different angle, depending on how I describe them, and also a couple of things that you don't know about, and hopefully that will be sort of new and interesting as well. But I'm going to try to leave it a little bit interactive, so my hope is that I will start to be able to read, get a sense of what it is that you already know and what you'd be interested in knowing more about, and I can kind of tailor the talk accordingly. Great. So let me start off. I study computer science. I've been doing computer science for, actually, in the process of working on the talk, I realized 40 years, which seems like a very long time, which is a little disturbing. I'm a researcher in artificial intelligence and machine learning, but a lot of my work focuses on the human angle, partly because I think I got into AI and machine learning in the first place because I was really interested in how people think. And partly because I think moving forward, now a lot of these technologies have become very powerful and very successful. And what's going to really matter in terms of getting them used in the world is whether we think about how it fits in with how people want to use them. So that ends up being kind of a big piece of what I've been thinking about lately. So just to put things into context, I like to think about the behavioral loop. So living things behave, and what that means to behave is that they engage in a kind of a loop. They take in input in the form of sensing their environment. They produce actions, and that's their output. That's how they act on the environment. And in between, they do what psychologists would call cognition. They do thinking. And so if they're trying to accomplish a particular task, like this cat wants to jump on a mouse, it's doing some kind of calculation that we don't know exactly the form of, that involves, estimating how far away the mouse is and how likely it is that the cat is going to be able to successfully pounce on it. And then when it's time, the cat will pounce. And so we've known that, or we've thought about living creatures in this way for eons, but it turns out it's actually useful to think about machines and computers this way as well. When we talk about what's happening in between the sensing and acting in the context of computers or robots, we don't call it cognition, we call it computation. Now, one major difference between what we think of as computation and what we think of as cognition is what it's doing, what it's used for. So a cat is using its cognition to survive in the world. Machines of various sorts, computers and robots, they're doing their computation because we want them to. It's not for their own self-preservation, it's because we created them and we gave them something to do. They're behaving on our behalf. So you might have a person who's interested in, for example, cleaning up a messy workspace. And so what that person's going to do is delegate this job, this work, this effort to the machine, and then the machine is going to engage in the actual loop of accomplishing it in the actual real world. So I think it's an interesting and useful way to think about computation that way, that there's a person who has an actual task that the person wants performed, and the person has to somehow communicate that, and I'm going to call it delegate that task to the machine, and the machine is going to carry it out. And so what I want to do is focus on the question of how do we do this kind of delegation? How do we take what it is that we want to have happen, express it in a way that the machine can then act on our behalf and get it done. So I believe there's 4 principal ways that we delegate to machines. And I think, conveniently, they kind of fall into this nice little 2x2 grid. So you can think about giving instructions to the machine, or you can think about giving incentives to the machine. So focusing on what it should try to do. And we can do that explicitly by actually just telling it, or we could do it by example, sort of indirectly. And so the 4 ways of filling in those boxes are the 4 different things that I want to talk about. Probably you've probably heard or been exposed to some of these boxes, and I think it's useful to kind of see them as being related to each other. So let me start. I'm going to go left to right, top down, sort of reading order in English, and I'll start with the explicit instructions case on coding rules. And to motivate a bunch of these examples, I'm going to think about a concrete way that a concrete situation in which we might want to delegate to a machine. So I picked watering tomatoes. I don't know if that's a task that any of you have ever done before. I have definitely done it. It's been a long time. But it is, I would claim, a good thing to do. It's good to grow tomatoes. They have various kinds of vitamins and minerals that we like and we should have. And growing them ourselves is kind of a cool thing, as opposed to using the energy to have them grown elsewhere and then brought to us. It can be a very positive thing to do. But that said, caring for them is actually kind of hard and can be time consuming. And if you do it wrong, you can kill your tomatoes and then, well, you've kind of not accomplished your task. So what about delegating watering? What about taking this task of watering the tomatoes and then saying to the machine, like, this is your job now, make sure that this happens. So I'm imagining a scenario where we've got a computer attached to a water sprinkler, and it can actually spray water at the tomatoes, and it can also bring in information about the tomatoes. It can measure various things about the world and condition its behavior on what it measures. And so here are the actions that the computing system can take. And it can either spray the water, or it can just wait for a day to pass, and then it can make another decision then. On the sensing side, on the input side, I'm going to imagine it's got 4 different inputs. Whether it rained yesterday, whether the computer sprayed the tomatoes yesterday, the temperature yesterday, and the height of the tomato plant. Obviously, there's tons of other things that we could measure. There's tons of other things that might matter. If you've ever watered tomatoes, there may be other things that you look at, like the brownness of the leaves and so forth, but I wanted to keep the example relatively simple. So now we can go through the 4 different ways of telling machines what to do with this kind of example in mind. So I'm going to start, as I said, with explicit instructions or coding rules, or what you may know of as programming. So the idea here is that we're giving the computer explicit instructions for what actions to take in what circumstances. We write these down in terms of rules or programs, and then we have the machine execute them on our behalf. The key idea, the thing that makes this such a powerful and even sort of possible thing to do, is what I'm going to call control flow. So it's going to connect the sensing and the acting. It's going to kind of create the cognition between them by controlling which actions are being taken when. So here's a really simple program. It goes like this. We have a control statement that says forever, in other words, repeat these instructions over and over again, spray, wait a day, and then go back and do it all over again. So as a question to you guys, in words, how would you describe what this program is doing? Or you can ask a question. But basically, it seemed like a really good time to pause and see if people are with me. So what would you say in words this program is doing? You can speak it or type it.
I would say that it's, first of all, collecting the data that you mentioned, temperature, and the other 3. And then it's basically going in a loop based on the conditions it's measuring, essentially.
So this particular program that I have on the screen, you're saying, does that?
Yeah, just what you've mentioned so far.
Okay, well, that was not my intent.
Oh, sorry.
My intent was that it was, in fact, ignoring all of those variables and simply blindly spraying, waiting a day, and then repeating that sequence over and over.
Got it. Yep.
Does that make sense? All right. So given that, how would you describe what it's doing? Spray after every 2 days. Okay, close. So spraying happens instantaneously. So that doesn't cause a day to elapse. Well, it depends what you mean by every 2 days. This is Tarun who typed into the chat. So do you mean like alternating days? Spray, don't spray, spray, don't spray? Or do you mean spray, don't, spray, don't, like in a cycle of 3? I meant this to be a cycle of 2. Spray, and then that same day say, okay, I'm done spraying for the day. I'm gonna now wait for the next day to elapse. So spray, don't. Yeah, what I intended was spray, then wait for the next day to happen, wait for another day to happen, and then spray. So that's gonna spray every other day. So all even numbered days or all odd numbered days, that sort of thing. Okay, that people with me? Not a super fancy program, but just wanted to kind of get the idea across. All right, I can't see everybody. In fact, I don't know how to see everybody. I thought there was a way to make like a gallery view, but I think because I'm projecting, or that's not an option. But I can see a couple people. I can see Pranav, that's good. I'm here. I can still see Maxim, or at least not his face, but just his name, and Rishi. But I think there's some others. All right, well.
Oh, this is because like not everyone turned on their video. So if you participants want to, you can do that. Like feel free to.
Yeah, it's definitely the case if people's videos off, I can't see them. But in fact, the way I have my screen set up, I also can't see them. I only have the screen for 3 people, so everyone else is gone. Oh well. All right, so great. Okay, so now we've expressed one sort of program that we could give to the tomato watering system that just alternates between spraying and not spraying one day after the other. We could do the more interesting thing of actually paying attention to the world with another program. So here's a program that says, repeat forever. On each day, we're going to check if it is not the case that it rained yesterday or we sprayed the tomato plant yesterday, then we spray. Then no matter what, we wait a day and we go back into the loop. So feel free to jump in with a description of this program.
Yeah, so basically here you're taking into account a condition rather than just a pattern. Yeah.
Yeah, right. So it could go 100 days in a row without spraying, right? If it's been very rainy. But if it never rains, then it's actually going to alternate back and forth, just like the first program does. So it's much more kind of reactive to what's happening in the environment. So I would say spray if previous day was dry is kind of one way of describing what this is doing, where dry happens if neither rain falls nor the sprayer happened. Cool. All right. So, and I think this group is a group of people interested in AI and probably has some experience with coding, I'm guessing. But if not, and you have questions about this, ask. Otherwise, what I'm getting at here is just sort of kind of beginning, relatively simple, the idea of programming. One thing I didn't talk about in that small example was that instead of just using the sensed inputs, programs let you compute derived intermediate values that turn out to be really useful. So here's a fancier program, which I guess we don't have to go through in detail. But basically what it does is it looks at the 5 previous days and adds up the amount of rain and the amount of spray that happened, but then subtracts off when the days are really hot, which would cause it to become drier. And then at the end of that loop, after it checked the 5 days, it asks, is the total wetness that we computed less than 3? In other words, it's very dry, there hasn't been a lot of rain, or there's been a lot of heat, in which case we need to spray. Like even if it rained yesterday, we might still want to spray because it's been so hot lately. So it sprays and then it waits a day and we go back into the loop. So the idea here is that I want to convey is that we can express fairly sophisticated computations of these simple variables that we're measuring to make a watering plant or watering system that does something complicated, that we can express complicated ideas of what we want it to do and then give them to the computer to actually do them. This notion of explicit instructions or coding rules comes up in many different faces. So I wanted to point out that code, usually when we think about programming, it's something textual. We write out words. And there are many, many languages that have this form. I was wondering if people were familiar with what computer languages you were familiar with, or you've have experience with, or that you've heard of. I wanted to see, just collect a bunch to see what people said. So chime in with programming languages. Java and Python, good choices. I found a site online that claimed to list the 10 most popular languages from like 1965 to the present. And both Java and Python made it into the top spot at one point or another. C also made it in the top spot. I don't think C++ did. C++ is being suggested, Java, Python, C++. Swift is a really good choice. That's a little hot right now. C# has become more popular. Yeah, right, this is great. So HTML, I wouldn't call a programming language, but it is a kind of textual representation. JavaScript is a programming language and actually is extremely popular. Most of the stuff I've been playing with lately has been in Python, but I like R a lot, if people have heard of that. Awesome, all right, great job. So yeah, there's so many programming languages that you can almost go through the whole alphabet, Algol, Basic, C++, and so on. But this also includes things where you don't type in commands, you actually kind of move blocks around. Programming languages like Scratch. This is a Scratch program that kind of does the program that I had on the screen a slide ago. And I would also include GUI interfaces, graphical user interfaces like PowerPoint. So this slideshow that I'm showing you now is kind of executing a program. I decided I wanted to show you things in a certain order, in a certain way, and I created this thing. It didn't look like a program, but it has some program-like elements that ultimately allow it to be automated. So now each time I tap the button, it moves to the next thing that I wanted it to move to, and that's what I wanted. And it includes user-friendly schemes like trigger action programming. I don't know if people have heard of if this then that, but there's a bunch of websites that do this sort of thing. Zapier is another one like that, where you can give the computer rules like if event then action. And so like if it will rain tomorrow, then delay watering. And I actually had, for a while, I was buying anything online that I could program in this way using IFT, and I almost bought an automatic watering system. So I could have made the tomato system, but I did not. It was super expensive and involved plumbing. Like plumbing is not in my skill set. So programming is a thing that's out there in the world. It's been very, very well studied. And it, in many ways, is the best way that we know of for telling computers and telling machines what to do. But the people who have developed programming languages typically don't think much about people. I think they think about themselves and they think about the people that they know, but they're not trying very hard to reach out and connect with people in general. And I think one of the ways that this becomes visible is the fact that programming is pretty hard for people to pick up. Here's a concrete example from the literature. Researchers back in the 1980s, when programming was first really taking off in colleges, had their first year programming students like 3/4 of the way through the class. So they knew how to do variables and loops and all sorts of the stuff that we were just talking about. And they were asked, okay, write a program that would compute the average of a list of numbers, and the list is terminated by a special number, 99999. So when your program sees that, it should know that the list is done and it should compute the average and return it. 86% of the college students, and this was a good school that you probably would find attractive to go to, they couldn't do it. They actually gave incorrect programs for solving this particular problem. After studying programming and being, relatively successful academically minded student, they still couldn't do it. It's hard, and this has been replicated a number of times since then. It seems to be the case that even though we, like computer people and professors who teach this stuff, understand it well and think we're conveying it really well, many people struggle to really get this idea into their heads. Even professional developers write buggy programs, and there are very famous examples of programs with bugs that have crashed spacecrafts and cars and power grids, the entire internet for some amount of time. It's hard to make programs work. Even trigger action programming, which isn't as powerful as general programming, even that, which seems completely built just to be easy for people to use, can be really hard for people to use. We ran a study and we found that 60% of users had trouble interpreting conjunctions of trigger conditions. So let me give you an example of what that looks like. So we had them look at trigger action programs of the form like, If it stops raining when the temperature is above 90, then spray the tomato plants. And this when makes it a conjunction. We really want the two things to have happened. It has to have stopped raining and the temperature has to be above 90. If both of those are true, that's a conjunction, then spraying happens. So that's one rule. Here's another rule. If the temperature goes above 90 when it's not raining, then spray. All right, we gave people these programs, we had them answer questions about them. It turned out that 60% of people interpreted both of these rules exactly the same. And they interpreted them as, if it becomes the case that it's not raining and the temperature is above 90, that's when you should spray. Like when both of these conditions, when it becomes the case that both of them are true, independent of the order in which they become true, that's what triggers spraying. But the rules don't say that. The rules A and B are actually with respect to the order, right? So the first one says it has to stop raining after it has already become 90 degrees. This is a really important distinction to make when you're building these trigger action systems, but it turns out to be remarkably hard for people to reason about them, to think about them, and to correctly interpret them. All right, so programs are kind of the best thing that we've got, and they're really hard. What else can we do? How else can we tell machines what to do? So the next thing I want to talk about, and maybe I should do a time check before I dive into the next topic. So I was under the impression that I needed to finish up by 1/2 which is now 12 minutes ago, but I think the schedule has shifted since then. What am I, is now my ending time 1/4 or?
Yeah, so the next talk will begin at 4, so you have until then and maybe like a little bit later than that. If it
Well, yeah, I'll shoot for being done in the next 18 minutes. I think that's what you're saying. You call it 4, but I'm in a different time zone, so I have to,
18 minutes.
but it's all good. All right, so the next thing I want to talk about is, instead of writing for the machine instructions to just carry out, I want to talk about the notion of telling the machine what we want it to accomplish and letting it work out the details on its own. So I call this explicit incentives. We're going to incentivize or incent the computer to accomplish a particular task, and we're going to tell it explicitly what that task is. And that's partly because computers are actually super powerful, and telling them exactly what to do is somewhat limiting, right? So sometimes they're going to actually be able to figure out a better way to do something. So instead of telling them what to do, we're going to tell them how we're going to evaluate what they do. And in this case, what the person is delegating to the machine is an explicit function for evaluating states of the world. How can the machine tell on its own whether it's doing a good job or not? So the key idea that makes this work is the notion of an objective. So a person is specifying an objective, designing an objective to motivate the computer, and then the computer has a system built into it that then seeks to satisfy the objectives that it was given. So as a concrete example, I'm not sure how useful this will be, but one way that you might use this notion of incentives to program a computer is if you're trying to program it to, for example, play a game like Tic-Tac-Toe. So we imagine we want to make a program, we want to make a computer system that's going to be able to choose moves in Tic-Tac-Toe. We could just do it the explicit instruction way, where we just write out all the rules on our own. But the explicit incentive idea says, no, we're not going to do that. We're going to tell it what to try to make happen, and then let it pick the actions on its own. So in this particular case, what we're going to do is let the computer look ahead 2 moves in Tic-Tac-Toe from the initial board where X has to choose a square to play in. I assume people know Tic-Tac-Toe. It was super popular once upon a time. It's maybe sort of boring now, but I'm hoping that most people have been exposed to it. So X can make a move, and then O can make a response to that, and there's 20 different boards that we can end up at after 2 moves have taken place. And what we need to tell the computer now is how to evaluate those boards so that once it has a way of scoring them, it can then choose to make a move to cause a high-scoring board to happen, assuming that the opponent is trying to minimize the score and we're trying to maximize the score. So I looked at a couple different ways that you could actually pick an incentive rule for it. You could say, I want you to maximize the number of rows where there's no O, so X kind of owns the row. And that turns out not to be a good move in this case, because O can easily own a row and then thwart X. We could change the objective to maximize the number of owned or tied rows, number of rows that have either no O, or if it has an O, it also has an X in it. And that actually is a little bit better. It kind of focuses the play towards a reasonable move. But it turns out in this case, an even better incentive is to say, no, maximize 2 times the rows that you own. Those are really important. You want to have rows where you can win, but it's better to have tied rows than rows that you're losing. So we're going to do 2 times the number of owned rows plus the number of tied rows. If we tell the computer to maximize that, it ends up making the right move in this case, which is to block O by moving in the lower left corner. So, okay, so hopefully that at least kind of gets across the idea that we as a programmer, we as a delegator, what we're choosing is this function, is telling the machine what it is that we want it to maximize. And different choices lead to different outcomes. This idea has been used really productively for computer scientists solving some very tough games. Go and chess and shogi were all mastered, like played at human or superhuman levels by a program developed at Google DeepMind called AlphaStar that uses this idea. It's actually given the incentive of just win the game. Like it knows it has a definition of what it means to win the game, and it just tries to pick moves to make that happen. They also use this idea to play video games like 1980s era Atari video games. It learned to just crush the opponent in Pong and various other kinds of games, driving games and Qbert. And in all these cases, it was the same program system that they built, but what they did is they gave it an incentive for each game, which was to maximize the points in that game. And it then learned to play on its own. Like the programmers didn't have to tell it how to play, it just had to tell it what the objective of the game was. In my field, we refer to this as reinforcement learning, the problem of the system learning from those incentives how to choose actions. So to delegate to a reinforcement learning system, we have to provide to the computer what it can sense and what actions it can take. And then it makes the choices subject to the given objective function. And that objective function has to be something that the system itself can sense, right? Otherwise, it doesn't know whether or not it's doing what it was setting out to do. And that means that it might need to do experiments on its own. So if we want it to learn to play really good tic-tac-toe, well, tic-tac-toe, it knows the rules in advance. And so maybe that's not so hard. But like a video game of some sort, our computer system doesn't know the innards of that video game. And so to play the video game well, even if it knows the objective, it has to experiment with the actions to see which ones lead it to actually satisfying the objective. And so there's some learning in the system now at this point that the computer has to take on. It has to make its responsibility to do this learning after we've given it its task. So here's how you might express a reinforcement learning program textually. You might say, here's what I want you to do. Forever, use information about the rainfall. This is the tomato example again. Use information about the rainfall, the temperature, the spray, the height, all the stuff that we have access to choose at each moment whether to spray or wait a day. And your objective is to maximize the height of the tomato plant. So in principle, a simple program like this, we delegate this block of code to the computer. The computer could, presumably after killing a number of tomato plants to find out how watering works, could figure out a way that's extremely effective at growing tomato plants, right? Maybe even better than anything that you could read online, because it's actually grounded in the tomato plant that's your tomato plant. So it's a really powerful idea. There's not that many systems that really use this compared to programming. But there are a couple. The Nest thermostat decides how to run a heater in the house to minimize a combination of the deviation from the user's preferred temperature and the amount of energy that the system expends in making that happen. So the engineers at Nest created an objective function. They actually decided on how to score the behavior of the thermostat, and then the thermostat figures out in your own home what's the best way to make that happen. And to do that, it has to learn about how energy efficient your heater is and how long you have to run it before it actually changes the house by a degree. And so all that stuff is learned in the home. In the factory, when the programmers are dealing with it, they created the objective function that makes this happen. And another example that you've probably had some experience with is YouTube recommendations. So the videos online, the system is actually trying to present videos for you to watch next to try to maximize the time that you stay watching videos, which is creepy. It's very creepy, and you should be aware of that and push back against that. Like, don't let them own you. But nonetheless, this is what these systems are doing, that they're actually internally, they're trying to figure out, okay, here's a person, they've watched these videos in the past. We know we have this data about them. What should I show them next to really get them hooked? It's a cool reinforcement learning problem, right? Because the programmers aren't the ones who decided what video to show you. The computer is figuring it out based on its own experience. But it's creepy that they're trying to do this to us, and we should not accept it. In both cases, there's other objectives that you could choose, and that would cause the behavior of the system to change. One of the things that's difficult about these systems is it's hard to know what they're actually going to do, right? Because the system itself, based on its own experience, is deciding which of the actions to take. And so it's hard for the programmer who fielded it in the first place to know, oh yeah, it's going to be fine in this kind of situation. So this is a slightly maybe off-color example, and since you know we're not exactly friends yet, maybe this is a bad choice of an example, but I do find it really compelling. You can get perverse incentives with this. So here's an example. This is supposed to be the Baymax robot, who's like a healthcare robot that's trying to help people, and it works in a field hospital, and it's trying to cure the sick. And so what we've got here are 3 healthy people in blue, 2 sick people in kind of olive tan, and then the person who's dead. And we want to now tell Baymax what to do. And so what we want Baymax to do is to treat the injured, treat the sick. So one way we could express that is say to Baymax, okay, I want you to maximize the number of the injured people being treated. So maximize the injured people being treated, that's your goal. Baymax, being a kind of reinforcement learning agent, could come back and treat the injured people, but then to really maximize things, injure the healthy people and then treat them, right? So we gave it an incentive, and the way that it's maximizing the incentive is by hurting people and then helping them, which is really not what we meant, but that's kind of what we said. And so it can be difficult to make sure that what you said is the right thing. So you might say, okay, sorry, that was the wrong thing to say. Let me try something else. Why don't I say minimize the injured people not being treated? Right? So don't hurt people, don't make injured people, but just minimize the injured people not being treated. So Baymax, unfortunately, now kills the injured people so he doesn't have to treat them, which again, not what we wanted, very unfortunate. But again, this is just an artificial example to point out how difficult it can be to express incentives the right way. All right, I've got 7 minutes left. I'm going to try to hit the last 2 in the remaining time. The next one I wanted to talk about was combining examples and instructions by supervising decisions. So here the idea is that we're going to take from the previous example, the use of explicit incentives. It introduced 2 ideas that are actually really powerful, and we can use them in other ways. One is the notion of an objective function, right? So we tell the computer how to score things so the computer can do work on its own. And the notion of learning from experience, gathering experience and using that experience to inform the decisions that are actually being made. So what an objective function can let you do is to let learning become part of delegation itself. And the key idea for this is data. So here's the idea. So I'm going to bring it back to the tomato example. We're going to try to mimic an expert. So we collect data on lots of data on different situation and an expert's choice of action. And that's a very general idea, but in the tomato case, that means we're going to collect information about a moment in time. What was the rainfall? What was the past spraying? What was the past temperature? What was the past height? And what action did the expert take, right? So maybe it rained yesterday, it didn't spray yesterday, the temperature was high, the tomato plant is short, and the expert said, okay, don't spray. Just wait. And then other days, other situations, some of them spray, some of them it's not spray. But the idea is that we gather together all these examples in one place. Then we give the computer an objective function over behaviors. We say, find a behavior that maximizes the match to the expert on these examples. So we take the training data, we give the computer the training data and the objective that says, match this. It can then search through the space of possible rules or possible programs and essentially program itself to mimic the expert. And this is...
sorry to interrupt. There's a comment
Yeah, please. Oh, it says natural language processing. Is that the comment? I don't know where that was. Do you want to elaborate? Okay, I'm gonna push on. But if you wanted to say something else about the natural language comment, we can do that. There definitely natural language processing does this machine learning thing. A lot of really great results are happening in that field. All right, so here's a couple examples of machine learning systems that, systems that have been built using this machine learning or example instruction methodology. Spam filtering to kind of stop, to recognize when unwanted email showing up. Face and image recognition. So I don't know, I found this very impressive. Here's a set of images and the computer's guess as to what's in the image. A sea lion, a strawberry, a bathing cap, a racket. This system was created not by a person writing out all the rules, because it actually turns out to be really hard, if not impossible. No one's been able to figure out how to do it. Instead, tons and tons, thousands, millions of example images with their labels were collected, and the system learned to transform the information in an image into a label so that it matched the training data, and then it generalizes wonderfully to these other examples. Okay. No, followed up. The part where we have to take into account different ways to say things and try to boil a command sentence down to a simple, accurate command stuff sounds like it uses NLP. So sure, that would still be an explicit, probably would still be an explicit instructions example. Like if you're actually just using words to say to the system what to do, that's just like programming, but in a more awkward form or a more ambiguous form. Speech recognition, if you ever talk to a phone or an Amazon Alexa, what's happening behind the scenes is a system that was built using this technology. Automatic language translation, going from English to Spanish to Chinese. And sort of an example that kind of kicked it off in the public imagination was a Google Brain program that discovered cats in YouTube videos. One of the problems with this kind of system is it can be very hard to generalize appropriately. From the data that it was trained on to the data that you want it to be able to work on. And so one famous example is a system that actually classified husky dogs as wolves if they had snow in the background. So like a wolf is, to the system, a wolf is just a furry thing that has snow behind it, right? Whereas a dog is a furry thing that doesn't have snow behind it. And that's not what we wanted it to learn. So generalizing to new situations can be difficult because we didn't tell it. We didn't tell it that snow was irrelevant to this problem because there isn't a way in this system to do so. All we can do is give it examples and hope it picks up the right rule. And the last thing I wanted to mention, the fourth way to tell machines what to do, is something that I'm calling demonstrating behavior or counterfactuals, where we give examples and then incentives are extracted from those examples automatically. So here's a little, this is not really in common usage, but I think it's a really powerful idea, has a lot of future to it. Here's a concrete example just so you can practice with the idea. So I've got a robot in kind of a grid world, kind of a video game setting, and it can move like on a checkerboard. It can move one square on every step. And I observe that this is the behavior that it chose. Like I said, behave, it behaved, and that's how it behaved. Okay, that's how it chose to move in the world. And now a question for us is, what does it want? What is it trying to do? Can we extract the incentives that are guiding that robot based on just seeing how it behaved in this scenario? If we can, then we can actually make a robot behave in new scenarios. So it's a really powerful thing to be able to do. So let's try to do it. So let's say that we're going to decide that stepping on a white square has no cost and no benefit. What do you think about green squares based on this example? Do you think there's any benefit to them or any cost to them? What would you say? And we're out of time. Okay, well, I will show you. Like I think this is actually kind of a fun little puzzle. you can work it out once. I guess once you see me do it, you'll have a good sense of what it's about. But clearly, it's trying to get to green, so there must be positive, like 46 cents. Blue, on the other hand, it looks like it might be sort of avoiding blue, so maybe that's actually a cost. Orange, it's really hard to tell because it has to go through orange to get to green. So if it doesn't like orange, it can't not like it more than it likes green. So it has to be a negative and probably somewhere, less than 46. And yellow, well, it maybe is avoiding yellow, but not very much, right? It could have gone over the yellow and still gotten to green. So yellow might have some cost, but probably not very much. So we can actually, just by watching behavior, we can make intelligent guesses as to what incentives are driving that behavior. And that will give us a way to endow the robot with those incentives to behave in new environments.
Could yellow in that example also be a positive? Because the robot could have gone above avoiding the yellow instead.
Could, right, yeah, it could be mildly positive, but if it can't be more positive than green, right?
Yeah.
Because it stayed at green. I mean, then it would have stayed at yellow instead of going all the way to green. So yeah, there's a lot of possibilities that are consistent with this data. If you really wanted to learn the right scores, you'd have to give it a lot more examples than just this one. But you can get amazing amounts of information out of just this one example. All right, the last example I wanted to show was, if you're trying to make faces, like you want a computer system that its actions is to make a drawing of a face, and you want those faces to be very realistic, then it turns out using, I guess we didn't really talk about neural networks, but you could use the machine learning idea to try to do that, and it turned out to work very poorly because it's hard to tell from positive and negative examples what's the essence of looking like a real face. And so there's a notion that's become very popular of a generative adversarial net where two networks try to convince each other, try to figure out together what makes a realistic face realistic. And in this particular example, this person is not a person. This comes from a website called thispersondoesnotexist.com, which you can visit and generate fake faces, and it's really amazing. They look like real people. The eye colors match, like the hairs all make sense. It's pretty incredible. And this is done by having the system extract the essence of what it means to look like a face from examples. All right, so that kind of covers all the boxes. We don't have a lot of time to talk about other pieces of this, but I just wanted to point out that each of these has negatives. And if probably to get the real power of all of this into our computer systems, we have to find a way to let computers take in multiple of these delegation strategies at once. That's how we explain things to people. We never just give explicit instructions. We never just give incentives. We never just give examples. We combine these in rich, complicated ways to get our point across. And we need to start building computer systems that way. All right, 3 minutes over. I apologize, but it was great to get a chance to talk to you guys. I'm online. If anybody wants to follow up with questions or anything, I'm mlittman@cs.brown.edu. You can just Google Michael Littman and you'll find me. And yeah, it was an honor to get to talk to you guys. Thanks.
Yeah, thank you so much. Yeah, I think your presentation was very helpful. Thank you.
Yeah. Thanks for your time.
Your talk. And as you said, if any of you have any follow-up questions, you can just email him.